In lecture B now, we're going to look at some basic applications of differential equations. We have done that before as well, but we'll do it again now. Probably the most basic kind of application is to free fall in physics. Free fall with the acceleration due to gravity being the only acceleration, the force due to gravity being the only force. So this is at a constant acceleration. So you got a mass, m, falling through the atmosphere, maybe it's a rock. The force due to gravity has got magnitude m times g. Magnitude of the force is m times g, where g is the acceleration due to gravity in standard units, about 9.8 meters per second, 9.8 meters per second squared. If we decide to take the positive direction to be upward, then the force is directed downward, it would have a negative sign. Newton's second law, F equals ma, could be written then as negative mg for the force equals the mass times the acceleration of the mass, which, with respect to y being the height, would be the second derivative of the height with respect to time. So this is a second order equation. It simplifies. The m's cancel. And we can solve for y by integration. Though it might be nice to think of the second derivative with respect to y as the first derivative of the velocity with respect to time. Second derivative with respect to t. It's the first derivative of v with respect to t, where v is the upward velocity. That can be solved by direct integral. It's really a basic antiderivative problem. Find a function whose derivative dv dt is negative g. Just integrate. V is going to be negative g times t plus some integration constant. If you label the initial velocity to be v0, that integration constant will be v0. Because when you plug in t equals 0 here, that goes away. V of 0 is v sub 0. V, though, is a derivative as well. It's dy dt. So we can integrate once more. We can integrate twice with the second order equation to find the height as a function of time. Y is negative g over 2 t squared plus v0 times t plus the initial height, which I'll call y0. So what I've done here is not really solved for the general solution. I've solved what you might call a generic initial value problem with the conditions that y of 0 is y sub 0 and v of 0 is v sub 0. If I think of y sub 0 and v sub 0 as being fixed constants, then this is one answer, one function that solves the initial value problem. Okay? That's your answer. What does it mean? Well, if you've got positive initial upward velocity, if v0 is positive and y0 is positive, your graph is going to look like this for y as a function of t. And you can find things like what time does it reach its high point, what time does it hit the ground, that kind of thing. You can find those kinds of answers once you've got this function. Another basic application of differential equations is to population growth. The simplest model of population growth is that the rate of change of the population with respect to time. So y here is the population. It's a function of time. and dy dt is its derivative, its rate of change, is proportional to the size of the population. There's some constant of proportionality, call it k, where this is true. Think about this again. The rate of change of the population with respect to time is what the derivative represents. By saying these are equal, you're saying dy dt, that rate of change, is proportional to y. The more people there are, the more babies that are born. The more rabbits there are, the more babies are born. That's a basic, reasonable sounding assumption, right? You can separate variables to find your general solution, but you don't have to. This is easy enough to guess. That a general solution would be any constant times e to the kt, and that would be correct if you think about it. That would be a function whose derivative is k times itself. When you differentiate it, the chain rule is going to give you an extra factor of k. Its derivative is k times itself. It solves the differential equation. If you add an initial condition in here, y of 0 equals y sub 0, or now y sub 0 is not a height, it's an initial population. That actually implies c is the same as y sub 0. So if you think of y sub 0 as a fixed number, then you think of this as one function, your unique solution to the initial value problem, consisting of this differential equation and that initial condition. It's an exponential growth function. K is positive here. The graph looks like this as a function of time. You've got exponential growth in the population. That typically is pretty realistic for a short term, say 5 to 10 years for people, maybe 5 to 10 months for bunnies. Okay? For a short amount of time, this is typically pretty realistic. In fact, you can even justify it as a constant percent rate of growth as well, leading to a model like this. But in the long run, it can't be realistic. Your graph can't be increasing and concave up forever. You're going to run out of room for one thing. You're going to have overpopulation, causing starvation and wars and that kind of thing. Over water, could be in our future, wars over water. I mean, there already are some wars over water in some countries. So this is not realistic in the long run, so people try to modify it to make it more realistic in the long run. This is called an exponential growth model. A more complicated and slightly more realistic one is called a logistic model. You're still going to have a constant k, so that the rate of change in the population when the population is small is essentially proportional to the population size. However, you have another factor in here, typically written like this. 1 minus y over n. N is called the carrying capacity. Of the environment. The idea being that if the population is below n, then growth can still happen. There's enough resources, enough food, enough space that growth can still happen. And if the population is above n, then the population dies off, or doesn't completely die off, but goes down to n. More people die than are born is the idea there because of overcrowding. Of course, this is still overly simplistic. Is there truly a constant carrying capacity for every environment? That can change because of improved food production, improved sanitation, that kind of thing can change the carrying capacity. So this is still oversimplified, but you might say it's more realistic than the exponential growth model. Solving this differential equation does involve separation of variables and using partial fractions like we did with our other example. In fact, in the other example, essentially we could think of it as being this example with n being, well, it doesn't quite match it. I was thinking n could be 1 and k could be 5, but it's of a similar kind of form. to the example we did where
dy dt was y times 5 minus y.
similar to that. Okay, not exactly the same thing, but similar. So you can use separation of variables. I'm not going to do the calculation by hand because it's not super pleasant. It is in the book. Let me point out what page it's on, in case you want to look there. There's an entire section actually on the logistic model, section 11.7. And the derivation is on pages 630 and 631. And actually they call their carrying capacity L instead of N, but oftentimes people do call it N. 630 and 631 you can find the derivation of your solution. Let's have Mathematica do it. So I'll go ahead and use DSolveValue to get my answer in the simplest looking form. And I think I'm going to add an arbitrary initial condition in here as well. So y prime of t equals, you need double equal signs again. K is an arbitrary constant, though positive. You've got y, but remember with Mathematica, you need to emphasize y as a function of t still. Times 1 minus y of t over n. I better not use a capital N here because Mathematica reserves capital N for numerical approximation. Let me use a lowercase n. And let me add an arbitrary initial condition in here. Y of 0 equals y0, like that. So conceptually speaking, you want to imagine y0 as something fixed, like 5 or 10 or whatever. Can Mathematica solve this differential equation? Gives you a little warning like it might not be right, but this does work. This formula right there, you can write that down. So we write it down, we want to write y0 as a subscript. Looks like for this logistic model that a unique solution of the initial value problem when k, n, and y0 are fixed can be written as, I'll write it like this, n y0, I'll use a capital N on the board. Capital N y0 e to the kt over capital N minus y0 plus y0 e to the kt. That evidently is a function that works. Does this graph look like you would expect? Let's see if the graph looks like what you would expect.
I just have a question. About the equation, could the quantity y subscript 0 times e to the kt, could that cancel since it's on
the top and the bottom? Not completely. You could divide the top and the bottom by y0 and e to the kt. And if you did, you could write the answer like this. And that is sometimes done actually. So I divided everything by y0 e to the kt. And in this fraction here can be also rewritten in a different form as n over y0 minus e to the negative kt. Would be another way you could write that. No, not quite. You write it like that if you like. Or like this. Either way is okay. You can do that.
I was just wondering.
Yeah. Let's see if the graphs of these things look like you'd think they'd look. So I'm going to do a manipulate of a plot of this kind of function as a function of t. T going from, oh, I don't know, 0 to 20, just to pick something. I think I'll keep my plot range constant. I think I'll include negative y values, even though that would not be valid for populations. And let's see, in my manipulate, I'm going to change, I got 3 animation parameters, n, k, and y0. Maybe I'll start k at point, I don't know, 0.05, let it go down to 0.01 and as high as 1. I'll start, and the carrying capacity at 10, go as low as 1 and as high as 20 perhaps, well as high as 15. And the initial population y0, I'll start at 1 and let it go as low as 0.1 or as high as 15. Well, no, maybe 20 for that one. Okay, so here's what the graph of the population as a function of time looks like for the initial values of k, n, and y0 that I picked. Let's look at a longer time frame. Let's go to 200 instead of 20. What's going on here? N is 10, is the carrying capacity. We see the population growing with a concave up kind of way at first, then leveling off its concave down toward 10, the carrying capacity. That makes good sense. If I let my initial condition increase, y0, the graph does this. And once you get y0 past 10, the graph does actually decrease toward 10 instead of increasing toward 10. And the k affects the initial population growth. The bigger k is, the faster the initial growth. Watch it here. But increase k, we'll see faster initial growth. Same initial population there, but faster initial growth toward the carrying capacity. So these graphs do look like you would expect based on how I described this model. And again, it's overly simplistic, but if you did try to apply this model to like the population of the United States, the idea would be you'd look at data, and you, based on that data, you try to estimate what k and n are based on some starting time. It probably wouldn't make sense to go back to the start of the United States because there's too much stuff going on in between that sort of messes the model up, like wars, for example. Diseases, like in 1918, there was a big flu pandemic that killed millions of people. So, I think my great-grandma died from it, actually. So there are complicating factors that prevent this from working over a real long term, but maybe over a 30 or 40 or 50 year timeline, it works pretty well. And so you could, based on data, you could try to estimate k and n and see how well this fits, and then you could use it for future planning. That's the idea. What are some other basic models that use differential equations? Another basic model is of cooling and heating. It's sometimes called Newton's law of cooling. It's sometimes called Newton's law of heating. Actually, you can think of it either way. I usually think of it as Newton's law of cooling, actually. Newton's law of cooling. Got some object, like a mug of coffee. The coffee has some uniform temperature at time 0. Is that realistic? Well, if you stir it after you've heated it up, it might be pretty realistic for the temperature of the coffee, the uniform throughout the coffee with stirring. And then you just let it sit there and cool down. It's in some room like this room that's got an ambient temperature. Not too warm today. I won't sleep with that. Might be 72 degrees in here or something, Fahrenheit. Some ambient temperature. The coffee's cooling in that room. What's the temperature of the coffee as a function of time? Making the assumption that it stays uniform, which, when it's cooling, probably the parts of the coffee fluid that are closer to the air do probably cool faster than the inside, but we ignore that kind of complication. And see how well this model does. You could have H be the temperature of the coffee at time t. So H is going to be a function of t. It should seem reasonable that the rate of change of H with respect to time should be proportional to, that means proportional to, prop means proportional there, proportional to what? How about the difference between the temperature of the coffee and the ambient room temperature? The greater that difference, the hotter the coffee is initially, the greater dHdt is in absolute value. The faster it's going to cool if it's really hot. The lesser the temperature difference, the closer dHdt is going to be to 0. That should make good intuitive sense. Does it make actual real life sense? I mean, will that happen? Evidently, I haven't done an experiment. Well, I think I did try an experiment actually with my daughter once. I think it came out okay. It's an okay model. When my daughter was young, I did some sort of experiment. Proportional to the difference in temperature. I could write that difference as H minus the ambient temperature. What should I call the ambient temperature? Should I just use a number? Like 72. Degrees Fahrenheit, I'm sorry, we're in America. 72 would be about 21 or 22 degrees Celsius, something like that. We do try to use metric most of the time. Would the proportionality constant, if I write it like this, would the proportionality constant be negative or positive? If I write the proportionality this way. If H is bigger than 72, it's starting out hot. Is dHdt going to be positive or negative if it starts out hot?
It's going to be negative.
It's going to be negative. But that'll be positive, so you need a negative constant of proportionality. You can emphasize that by writing dHdt equals negative k times H minus 72, where k itself is positive, so negative k is negative. There's your model. Can we solve it? Yep. Separate variables. Divide both sides by H minus 72. Keep the negative k on the right maybe. Multiply, quote unquote, both sides by dt. You can write dH over H minus 72 equals k, negative k dt. Integrate both sides. You don't have to bother with partial fractions. Looks like we're going to get a natural log of the absolute value of H minus 72 is negative kt plus C1, I'll call it. Zoom in. Exponentiate to get rid of the natural log. E to this gets rid of the natural log. Gives you e to that. E to the C1 can be thought of as a C2. And then if you get rid of the absolute value sign, you can use a C instead of a C2. And then add 72 to both sides. I'm doing like 3 steps at once here. Exponentiate. E to the natural log of this is just this. E to this can be written as e to the c1 times e to the negative kt. E to the c1 could be thought of as c2. You can get rid of the absolute value signs and call it c instead of c2 for the constant. Then add 72 to both sides to cancel the 72 on the left and solve for h. So 3 steps essentially there. But again, there's a general solution. You got an arbitrary initial condition, h of 0 equals h sub 0. Plug in t equals 0, you'll get this equation because e to the 0 is 1. The c must in fact be the initial temperature of the coffee minus 72. By the way, I'm using h for hot. The coffee's hot. That's what I'm using for h. Gotta humor myself somewhere, right? And then replace c with that. Your unique solution of an initial value problem where the initial coffee temperature is h sub 0 would be 72 plus, in parentheses, h0 minus 72 e to the negative kt. What is k? That depends on the situation. If your coffee is insulated, like this, k is probably not very big. On the other hand, if the coffee's in a thin cup, it's not styrofoam, then k is probably fairly large. The coffee's going to cool rapidly in the thin cup and cool not so rapidly in the insulated thing. So the value of k depends on the situation. Also, different fluids would cool at different rates. You know, coffee is probably going to cool faster than hot Jello. Hot Jello would melt though. I don't know. Then hot tar, for example. You could solve for k if you were told what h0 was, for example, maybe 150, and if you were told that h of 2 was 130, meaning your temperature is 130 degrees after 2 minutes, if times in minutes, you could solve for k. What would the graph look like? It would look like this. Here's 72. 72 is going to be a horizontal asymptote. Your graph's going to look like that. Exponential decay toward the horizontal asymptote. Actually, this exact same model works in the situation where you are heating something. If the coffee's cooler than room temperature to begin with, if it's been in the refrigerator, and you bring it into room temperature, the same equations work. But your initial condition would be below 72, and your coffee would warm up towards 72. But the same stuff works. If h starts out lower than 72, this is going to be negative. Times a negative is a positive. dHdt will be positive. The same equation works, and you could call it Newton's law of heating in that situation. It really is the exact same equation, the exact same model. Of course, if you're warming ice up, there are complicating factors like what happens at the melting point. It goes through a phase transition, and the increase in the temperature is not as fast, right? If I remember my chemistry correctly. Those phase transitions, it's not a smooth increase or decrease in temperature, because energy is going into causing a phase transition or something like that. So this is oversimplified in that kind of situation, though it's probably not too bad over a long period of time. Try one more. No. This model will be a preview of next week that I'm about to do. There are other basic models that I probably want to do next week as well. Another one that's coming to mind is called a compartmental model, a mixing model where we've got salt water mixing in with fresh water. I should have talked about that already 3 months ago or something. Okay. That'll be another kind of model we'll do. But I just want to introduce you to what's called a predator-prey model. I guess we only have about 1 or 2 minutes here. Oh, these markers drive me crazy. Predator-prey model. There we go. Where you've got two interacting populations. And we saw that predator-prey model the first day of class where you had the rabbits and the foxes, right? Remember those dots? Some of the dots were eating the others. That was a discrete model, not differential equations. You can have differential equation models of predator and prey interactions as well. Let's once again say rabbits and foxes. It's a system of two equations telling you the rate of change of the rabbit and fox populations with respect to time. So it's not just a single differential equation, it's a system of differential equations. Just like you can have systems of algebraic equations, you can also have systems of differential equations. What happens if the rabbits are there in their fields and there are no foxes around to eat them? I just watched Zootopia yesterday. So perfect. I did, I'm serious. I didn't think about it until just then. The rabbits are there to just grow their happy way. There's no foxes. Probably it's exponential growth, right? Rabbits grow exponentially. There might be some constant, let's call it alpha, where dr dt is alpha times r in the absence of foxes. But what about if there are foxes? Actually, I read foxes don't usually eat rabbits, but we're pretending. The presence of f would cause dr dt to be less and maybe even negative if there were enough foxes. Maybe there's some other constant, call it beta, so that the interaction between rabbits and foxes causes dr dt to go down by this quantity. Why am I multiplying r times f? Essentially because, if there's lots of foxes but only a few rabbits, maybe the rabbits can hide, and so they don't really get eaten that much. On the other hand, if there's lots of rabbits and not many foxes, maybe rabbits can even overwhelm the foxes and they can't eat much. Okay? It's only if r times f, the number of rabbits and foxes is large, that it really gives a bad contribution to the rabbit population. So maybe it's something like that for the rabbits. And for the foxes, it might be some other kind of differential equation. In the absence of rabbits, they die off. Some constant negative gamma times f means the fox population dies off. That's a gamma there. It's not a weird looking 2. It's more typically written like that. It's a gamma is what it's called. So the foxes die off when there's no rabbits to eat. But when there are rabbits to eat, there's an interaction term that's got another constant called a delta, where this contributes positively to the fox rate of growth, because they have rabbits to eat. So alpha, beta, gamma, delta are all positive constants in a given situation. And we will look at this model in more depth next week. Enjoy your Thanksgiving.